Hello, hello. Who do I have here so far? Hi, Donna. Hi, Julia. Welcome, guys. Could you guys do me the favor? We can do this before anybody gets here. Will you let me know if you can hear me and see the presentation? So hopefully you see a screen that says triangles on it. And hopefully you see a video with a man who looks like me. Let's see. Thank you, Donna. Awesome. Good. Okay, so we're good to go. I was just thinking, and this is our built-in 3 minutes of screw around time, which is fun. I was just thinking that I think I spend more time visiting with people online and during the time of pandemic than I do not during the time of pandemic. Like I've been making more meetings. I've been doing these events. And it might be coincidental too, because I started setting up some other meetings that were just sort of, it happened to start close to the pandemic. But yeah, I mean, I'm, if anything, more social now than I was before we were, when we were allowed to leave the house. Anyway, how are you guys doing? Who else we have here? We got 3 attendees now. Elizabeth, hello, Elizabeth, welcome. Who else is coming in? I was on a big webinar today. I was a participant in a big webinar today for Teachable, which is the platform we use for our online courses. And the webinar broke like midway through. It was supposed to be an hour-long thing, and about 40 minutes in, it just like fried out. I mean, that's not the technical name for what happened, but that is what happened. And it was, I'm sure it was like their worst nightmare. And I'm really glad it wasn't me, and I feel sorry for them. Hi. I wonder if we'll have more people tonight, the same number we've been having. It's been fun. It's been a pretty good number, like a pretty consistent number of students this week in general. So I've been pretty happy with it. And I appreciate you guys being here so much. Oh, good. Grace, you got in. Yay. Good. Hi, Zoe, by the way. How many? We've been at, let's see. So we had, the first day we had like 26, which is, that's a really nice number. The second day we had, I think, a maximum of 17, but it might have been a little bit less than that, like 14 on average. And I was like, okay, well, this thing is going to, crash and burn. And then last night we had 20. So it was, I was like, okay. So now it'll be something completely unexpected to me. It'll either be, 1 or 400. Those are the two possibilities. But it is 5:30. People do come in like pretty much right on time, and hopefully they've learned that I start these things right on time. I'm really good at starting on time. Like, I'm fantastic at that part. That, no problem starting on time. Now, finishing on time, if you've been to any of the other events, you'll know that I'm not as strong at that. But I'm going to try tonight. This is the 4th webinar I've done, and the 4th time I've said that I'm going to try tonight. I'm really going to try to keep it to 20 minutes or less, which means I've got to get going. So this is a shape geometry lesson, and there actually is a lot of content. There is more content today than there's ever been before, frankly. Yeah, I mean, I'm a big fan of starting on time too. I think that's the right way to do it. Okay, so here we go. We're talking about triangles and how important they are. And the first question I'm going to ask is, well, how important are they? The answer is they were important enough that Carl Friedrich Gauss, that amazing mathematician who's already come up once earlier this week, and 2 of his friends, climbed 3 mountains to determine if triangles have 180 degrees. And the answer is they do, at least when you're on a plane. So basically, I was told this story. I thought Gauss was trying to verify that they did have 180 degrees. He was actually trying to prove that they didn't, that basically Euclid was wrong, that Euclidean geometry, he thought it was sort of, suspicious and bogus. And so they climbed 3 mountains. I'll show you the diagram here. This is this paragraph explaining it. You can read it. Maybe I'll read it too. But like, they, obviously these mountains are very far apart, climbed to the same height, measured out in directions where they could see each other, and then measured that angle, climbed back down. They did not have cell phones at the time, and added up the degrees. And it was it said at the end here, if Euclidean geometry is correct, then the angle should have sum to 180 degrees. To his disappointment, Gauss, he found that the sum was exactly 180 degrees plus or minus 15 minutes. So the 15 minutes is like, there's 60 minutes in a degree. So it's, plus or minus 1/4 of 1 degree, which is pretty darn close. And it was exactly 180 degrees. So it's pretty cool that they did that. And hopefully they had a fun day that day. Okay, moving on. We're going to learn everything about triangles. This is the plan. We're going to literally going to learn every rule about triangles. And then we're going to see, I think it's 6 sample problems. I think it's 6. It's either 5 or 6 that put these rules into play. So here we go, because that's a lot of stuff. Triangles have 180 degrees, as Gauss proved. Now, he didn't prove, he demonstrated. Those 3 angles are in a triangle. They must add up to 180. Yay. Next thing. This is my favorite rule that sounds really crappy, and then it makes perfect sense once you see it. The sum of the lengths of any 2 sides of a triangle must be greater than the 3rd side. Here's the demonstration. If I have sides of 5 and 3, 5 plus 3 is bigger than 7. Therefore, I can make a triangle out of it. Is it a pretty triangle? Is it an interesting triangle? Not especially, but it's a triangle, just because 8's bigger than 7. And then if you have 5, 3, and 9, you don't get there. The 5 and the 3 can't reach over the 9. Basically, it's not a triangle. So how do you build a triangle? You start with one side, and then you add in 2 longer sides, because the shortest distance between 2 points is a straight line. If you don't take that same path, you have to go the long way, then it's going to be a little bit longer than that shortest path. Okay, next one. Okay, so 2-dimensional measurement of triangle is area. That's I guess the 2-dimensional measurement of everything. Anyway, the formula is area equals 1/2 times the base times the height. If we had all day, I would derive this and show you the rectangle, but we don't have all day. We've got, why do I always talk about the time? The more I talk about the time, the less time I have. The height has to be perpendicular to the base, right? It's got to be at a right angle to it, otherwise it doesn't count as the height. In an obtuse triangle, you could end up with a height that's outside the triangle. We don't have time to see that right now. Stop talking about time. Oh my gosh. Okay, moving on. Okay, isosceles triangles by definition have 2 sides that are equal and 2 angles that are also equal. The grammar of that sentence is suboptimal, you might say. That's an isosceles triangle. The 2 legs going upwards, you can see they've got the 2 little hash marks on them. That means that they are the same as each other. And then the angles opposite them, right? So like the angle that kind of shines onto that side is the angle opposite. And those 2 angles must be equal as well. On these standardized tests, if you're told the 2 angles are the same, the important thing is that the opposite 2 sides are the same. If you're told the 2 sides are the same, the important thing is that the opposite 2 angles are the same. Okay, Pythagorean theorem. This is, vintage right triangle trig. So Pythagorean theorem, boy, I'm tempted to go complex, but I'm not going to. This applies to right triangles. I'm leaving something out. Talk to me later if you want to know the sort of like alternatives to the Pythagorean theorem that are kind of interesting, but I don't have time for right now. Okay, moving on. A squared plus b squared equals c squared. In every right triangle, that is true. Whatever your 2 legs are, if you square the first one and you add on the square of the second one, you will get the square of the hypotenuse. It always works that way. This is really useful test prep stuff. These triples are integers that make that statement true. This is a really nice little hack. I would memorize these. I would write these down on a note card. I would put them on a Post-it note. I'd put them on your bathroom mirror and basically like see these until you know them really, really well, because they can save you a lot of time and they can actually kind of solve a problem, before you have to do any real work. I'll show you an example of that in the sample problems. So these are the popular ones. I think 6, 8, 10 is probably the very most popular one, but 6, 8, 10 is just twice as big as a 3, 4, 5. 3, 4, 5 is the sort of essential starting point basic Pythagorean triple, and it's cool. 3 squared is 9 plus 4 squared, which is 16, equals 25, which is 5 squared. So that's why that's triple. This whole line, they're all multiples of 3, 4, 5. 5, 12, 13, another random one, kind of a fun one. Any multiple of that, so 10, 24, 26, you could just double all 3 side lengths. 8, 15, 17, that's one of my faves, my personal fave, Pythagorean triple, I'd say. Just so random and weird. and 7, 24, 25. I think they proved, yes, it is, you can verify that there are an infinite number of Pythagorean triples. That has to do with like the difference between squares being an odd integer, and that's a long story, but again, not going to say the word time, except I just did. One more thing, similar triangles. So similar triangles, I love the adjective. Similar means they look alike, they look like each other. So in this diagram, triangle ABC is similar to triangle ADE. And when you say that statement, you actually have to say it in order. But no, you need to say it in order, because you want to tell the person who's looking at the triangle which of the angles are the same as the other triangle's angles, and which sides are proportional to the other side. So like side AB is proportional to side AD, the way that side BC is proportional to side DE. Anyway, this is a lot of information right here. It's kind of basic though. I mean, this is just how much spelling out has to be done. The idea is when two triangles have two angles that are the same, well, their third angle must be the same, and you can figure that out because they have to add up to 180 degrees. And if they have three angles that are the same, then they're the same shape, and they will be proportional to each other in terms of their side lengths. You could have two triangles that were similar and in the proportion 1 to 1, which would mean they're also congruent, which is another vocabulary term which I'm conveniently leaving out of this presentation. But congruent triangles would also be similar because they're in the proportion 1 to 1. But you could have a triangle that is 2 to 1, twice as big. You could have one that is 3 to 2, 50% bigger than the other one. But once you know that, then you can use proportions to solve for missing side lengths. I think that's it. Oh boy, they got another one. Okay, special right triangles. There are two special right triangles, 45, 45, 90, and 30, 60, 90. I'm not going to make you memorize this now. In fact, you don't really need to memorize it at all. I guess the ACT doesn't give you this. You could put it into your calculator in the memory. That would be totally legal to have that information. I don't think it's built in. Some other stuff's built into the calculator. I should do a lecture on the calculators at some point for sure. But 45, 45, 90 is isosceles, which means it has two sides and two angles that are the same. And the convenient thing, and the reason this is a special right triangle, is that the hypotenuse is always bigger than the sides by a factor of root 2. It just works that way. In a 30, 60, 90 triangle, if you label the small side opposite the small angle x, then the side opposite the 60-degree angle will be x times root 3, and the side opposite the right angle will be 2x, twice as big as the small leg. And this is trig. This is like reduced sine, cosine, tangent trig, and it underlies the unit circle and all that business. If this information is presented to you on the SAT, you could give it to yourself on the ACT. So let's not worry about memorizing it. Let's just know that they exist, and even like know that the root 2 and the root 3 thing is out there. So when you see it on a problem, you can look for it and know that you're going to kind of plug that information in. You're going to want to use that information. Okay. All right, so here we go. 540. I'm going to give myself 10 minutes to do these questions, but I still have to work quickly to do it. And I do need my tools, my annotation tools. Whoa. You guys hearing that noise? Oh my gosh.
You'll need to unlock your iPhone.
Oh,
first.
Siri. Oh my gosh. Okay, every time I try to annotate, it's giving me this horrible noise. Are you guys hearing that noise? B. No. Wait. I think the noise is gone now. What was that? I'm on this new computer. No noise. Okay, good. Thank you. Anyway, boy, I'm never going to get through this if I go that slowly. Here's what we would do in this triangle. We know that the angles add up to 180 degrees in total. In the big triangle, I've got a 30 and a 90 marked by the right angle. This big angle, the whole thing must be 60 degrees. We also know in this little triangle up here with the 60-degree angle, this one must be 30. And if that guy's 30, and if its neighbor if the whole thing is 60, then C must also be 30. No, that was quick, very quick. Appreciate that. All right, so it's a warm up. Not totally soft, but not impossible either. All we needed to know was the first slide, which is what Carl Friedrich Gauss knew, which is that the angles in triangle add up to 180. Cool. All right, moving on. These will get more fun. Okay, in the figure above, AB has length 4 root 2. Let's write that in. Oh no, This thing is so noisy. That is so weird. I don't know. Like, as soon as I turn the tool on, it just starts making this like horrible beeping noise over and over again, and then it stops. So anyway, hopefully the computer gets better. Okay, good. Yeah. Okay, good. All right. I'm just going to ignore it. I'm going to pretend like you guys, you don't hear it. So nor do I. Side AB has length 4√2. This is what I'm talking about in terms of like looking for the special right triangle thing. The √2, I mean, there are ample clues here that this is a special right triangle, but the √2 is the best one because √2 shows up in the 45, 45, 90 triangle, and the test makers tend to do it that way, to basically like set it up so that the if you see a √2, it's going to be a 45, 45, 90. I don't think that I've never seen them be more rude than that and like introduce a √3 into one of these or a √6 into both of them. So basically, like, let the clues guide you. This one's isosceles right because you've got the two angles that are the same and the right angle, and isosceles right is a 45, 45, 90. And the 45, 45, 90 triangles, these guys, these side lengths we call S, and the hypotenuse we call S√2. So they must be 4 and 4. One other trick here is the area of triangle ABC. Whenever you have a right triangle, I would always use, and this is common sense on this one, but it depends. It doesn't matter which way the triangle is oriented. I would always use the two legs as the base and the height. And then we're going to use that other formula, which is base times height times a half. Oops, let's put the times in there. 4 times 4, and then put the 1/2 in front. Let's just do this as backwards as possible. How about that? And that's going to be 16 times a half, and that's going to be 8. That's going to be the right answer. And Noah had that answer half an hour ago. I have to go slow, Noah. I have to set a pace. I don't know, a slow pace. I don't know. Okay, moving on. I'm not going to hear any noises. Oh, skipped over one. Okay, it's going to happen. Can't hear it. Just can't even hear it. Okay. So to get from the subway station to her office, Farisa must walk 8 blocks due north and 15 blocks due east. Every geometry problem that describes something that you don't see, you want to draw it. So let's put those lines in place. This is the 8 north. This is the 15 east. Why do we ever walk in those cardinal directions? Because they're at a right angle to each other, and that's going to create a right triangle, right? So basically, like north and east are perpendicular to each other and always will be. We could talk about non-Euclidean geometry, but it's not going to show up in the tests. This is my favorite triangle. It says, what is the straight line distance between the subway station and her office? And it's the hypotenuse of that triangle. And if you know what you're doing, and if you know the special right triangles, you wouldn't even have to do the math. You'd be like, oh, that's an 8, 15, 17. As soon as I see 8 and 15 in the problem, I'm actually assuming it's going to be an 8, 15, 17. And like, that's not probably 100% true. It's probably 99% true. So whatever, you don't have to use that as a hack, but it could be one. Cool. All right, moving on. Someone's D. Noah, you didn't give me an answer on that one. Come on, man. Oh, okay. This is a classic. I was thinking about this problem earlier today when I was planning this lecture. I was like, I should do the triangle in the circle question. And then I was working with a student, Grace, hi Grace, who was doing GRE prep. Okay, so GRE is the test to get from college into graduate school. And guess what the very first problem was? This one. It just had a 60-degree angle, and this one has a 40-degree angle, but it's the same thing. So I'm going to label this thing. It says X is 40 degrees. Let's put a 40 on there. And the question is, what is Y? So this is actually slightly easier than that one we did. Make my degree sign better. There it is. Okay. This is a little bit of circle knowledge, but then the circle knowledge will play back into triangle knowledge. All the radii of a circle must be the same. That's actually the definition of a circle. A circle is the set of all points that are equidistant from another point. So you start at the center, you take a little string, and you draw all the points that are exactly that same distance around. That distance is the radius. If those two sides are the same, then these opposite angles must also be the same. And so the math we're going to do is 180 minus the 40. I think a bad handwriting day generally. What can you do? What can you do? Let's see, 1. Oh my gosh, see, See what I'm talking about? Look at that 4. What is wrong with that thing? And if those two angles are the same, I'm gonna make my little special angle thing to show that they're definitely the same angle. You can divide that by 2 to get the number of degrees in them, and that's going to be 70, and that's going to be the answer to the question. And every time you see a triangle drawn in a circle, I promise you that's what it's about. It's going to be isosceles. It's guaranteed. That's how that problem works. No surprises. Moving on here. I might actually make it on time. Don't get too excited. Okay. This question says the lengths of two sides of the triangle are 6 and 9. Which of the following could not be the length of the third side? The answer to this question is always going to be based on the sum of the sides. It basically, that rule, which was the sum of any two sides of a triangle have to be greater than the third side. What that rule really is how do we make a triangle, right? It's basically like start with one side, take another path from that point to this other point. That path must be longer because it's not the straight line distance. So if we're starting with 6 and 9, and if we know the rule is basically I need the sum of the small two sides to add up to more than the big side, the right answer is this one, because you can't make a triangle with 3, 6, and 9. It'd be like 3, and then it would be like 6, something like that. It's pretty good, actually. And then 9. And they're the exact same length. And if you put them on top of each other, they would just be sort of like sitting there flat. They would not pop up to make a triangle. If you added 0.001 to that 3, now you have a triangle. A very, 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 very skinny triangle, but still you have a triangle because the sum of the two small sides is bigger than the third side. What's the, okay. Follow-up question, don't have time for it, sorry. Follow-up question is, just think about it. What would be the greatest, what's the upper limit for the third side of this particular triangle? You're starting with sides of 6 and 9. What is the first value that third side can't be? Anyway, I'm not really asking that question. Oh, there you go. Thanks, Julia. Yeah. Oh, that's interesting. So yeah, so 15's, yeah. I like those answers, and this is me screwing around and not getting to my last question, but 15's the upper limit. It can't be 15. What could it be? Well, whatever's just beneath 15. If it has to be an integer, exactly, Noah, yeah. And then we could get into the discussion about the fact that 14.9 repeating is 15, and you can show it. You can prove it algebraically for what it's worth. But that's, anyway, you're right. Whatever is just underneath 15 is the largest side length you could have. Okay. I don't have time. Okay. This is the hardest one. This is the best one. This is where the magic happens. Triangle ABC above. What is the length of side AC? So if you're like me, you look at this triangle and you'd say, boy, that looks like a 30, 60, 90. I mean, I've got a 30-degree angle. And by the way, Julia, you're right. It just depends on if you say integer or not. You know what I mean? If the problem says it has to be an integer, then 14 would be the answer. Okay. You want this to be a 30, 60, 90. It's not a 30, 60, 90. Well, let's make it B1. So I'm going to go from point B. I'm going to drop an altitude down from there to there, right? That's the height of the triangle. I chose to draw that myself. These are right angles because I chose to draw it as a right angle. Let's see what happens. If this is 30 and this is 90, then that leaves me with 60 degrees on this side. Okay, cool, good, got 30, 60, 90. Let's draw some other conclusions. If that's 60 out of the 105 that are up there, I must be left with 105 minus 60, which would be 45. If that's 45 and this guy's 90, what's happening over here? This guy must also be 45. So out of nowhere emerged two special right triangles. Can I tell you how often this question has showed up on an ACT or an SAT, and when it shows up at the very end of the test as like definitely the most difficult shape geometry question on the test? Is it that hard? No, it is not. The trick on this question is to A, know that special right triangles exist, and B, make them happen. Drop that altitude and even know that the test makers love special right triangles as well, and be looking for them all the time. So once we know this, we would use the reference information or the information in our calculator, and it would tell you the side opposite the 30-degree angle is half the hypotenuse. The hypotenuse is the one opposite the right angle, which is the 12, which means that this side up here, its vertical side is 6, and this side's got to be 6 root 3. We're basically just, I have this memorized now, but you're just stealing this reference information from the test makers because they gave it to you. In the 45, 45, 90 triangle, these two legs must be the same. That's got to be 6 as well. We don't need it, but just for the heck of it, this guy's 6 root 2, because why not? And the length of side AC, oh, Grace, I learned this trick from you. I literally learned this trick from you, and I've been using it ever since, and I love it. That. Basically, like, draw the line segment and leave out the little, the spots where it's you have the number. Like, look how pretty that looks. It's so good. That side length is going to be 6 plus 6 root 3. Boom, right there. So it doesn't get any harder than that. That's as hard as it gets. Pretty manageable. The rules that I showed you are all of the rules you need to know. And the thing I would say you'd want to study, because I think most of that stuff I would say study the triples, make sure you know those, like, like don't sort of know them, right? You can always prove them to yourself on your calculator, but just knowing 8, 15, 17, knowing the hypotenuse is going to be 17. If you see 17 as the hypotenuse of the triangle, realizing it's probably an 8, 15, 17. And then also that how to build a triangle. Oh, and similar triangles too. Know that as well. Those are like the ones that show up on the hard questions, but they're not too hard, these triangle questions, I don't think. That's all I got, guys. 23 minutes. I mean, that's actually a little bit better. I mean, it's happened all week long. This has happened. I've thought it would be 15 minutes, and it was exactly 23 to 24 minutes long every single time. Thank you, Noah. Thanks, Antoine. I'm back tomorrow. I'm talking about punctuation. Yeah, totally right. Yeah, I set a new personal record. New PR today. We're talking about the M dash tomorrow, my favorite piece of punctuation, and it'll be fun. We'll see if I have 15 minutes to say about the M dash. I've got some ideas.